Okay, so a 10-pound sphere starts from rest at theta equals 0 degrees. So that's where it starts, and rolls without slipping down a cylindrical surface which has a radius of 10 feet. Determine the speed of the sphere's center of mass at the instant theta is 45 degrees. So when theta is 45 degrees, find the velocity of the center of mass. Yeah, I'm just going to draw the free body diagram because I highly recommend drawing it because they always give you some credit. When we're drawing the free body diagram, don't draw it over here. Draw it at a general angle theta.
You need to draw it where it is right now. After 45.
No, just at a generic angle theta. Don't put theta equals 45. Oh. Don't put special cases. By the way, there is gravity which is not mentioned. Okay, is that it? There's friction because it's rolling without slipping. And you're not told it's a smooth surface. Okay, now what we are told to find is we're given the initial velocity, which is 0 at theta equals 0, and we're told to find the velocity when theta is 45 degrees. Okay, now one way of solving this problem is, and if this had not taught you this chapter, is to use Newton's laws. So if you use the free body diagram, write the equations of motion in tangential normal coordinates, right? That's the right coordinate frame for this particular problem. And then integrate the equations of motion. You'll get a formula for v dot. Integrate that, you'll be able to find velocity. Okay, so you can do this problem using equations of motion. So I'll put this down, but I'll solve it using conservation. Use equations Okay, you can also try this later on. Now, the reason why I would use conservation of energy principle of work done on this problem is because whenever if you're given velocity at a particular point, at a particular position, and you're told to find the velocity at another position, so you can see that velocity, you need to find velocity as a function of distance, then it's always best to use conservation of energy and principle of work done. It just makes your life easy. Okay, that's the clue on how to go about using conservation of energy and not using equations of motion. Though both these methods will give you the same answer. So I'm going to use method 2, which is principle So there's another principle called conservation of energy, right? And we'll talk about it in the next section. We've done that in the past for particles. You could, in principle, use conservation of energy too. The reason why conservation of energy works in this case is because all the energy, all the forces in this case are conservative forces. Now you may say, well, there's friction. That's not a conservative force. But it turns out that the point of contact has 0 speed, right? The point which is touching, well, the bottommost point on the disk which is touching the circle is at 0 speed. So the work done by that force is 0, by friction force is 0. So you could, in principle, use conservation of energy. So let's just do it with principle of work energy, but you'll get the same answer using method 1, method 2, and method 3, which is conservation energy, which I'll not talk about. So the principle of work energy says that T1 plus U12 is T2. T1 is the initial kinetic energy at theta equals 0 degrees. We're told that it moves, starts from rest, so T1 is 0. T2 is half mvg square plus half I omega square. The reason I wrote this formula is because, well, there are three cases, right? Translation motion, rotation about an axis, fixed axis, and general planar motion. This clearly has rotation as well as translation, so I cannot use the first formula, half mv squared. I cannot use the fixed axis formula because this is moving. It's not rotating about a fixed axis like a pendulum. So I use the third one. So in this case, I can simplify this a bit by noting that rolling condition is Vg is omega g times r. In other words, this is V, this is omega. Then since this point is 0 speed, right, when a disk rolls without slipping, the velocity of point of contact is 0. So Vg is omega gr. So using that, I can write T2 is Vg square plus okay. Well, this is not given, but the inertia of a disk is mr squared divided by 2. So I'm going to simplify this a bit. See that?
I think the question was posed earlier, but I just want to go back to it. What's the difference in using this formula, the T1 plus U, some of the works, plus T2, versus the T1 V1 equals V2?
In this case, there's no issues. It's the same thing. It gives you the same answer. If the work done in this case U12 is equal to the change in potential energy for this problem. The reason why, so the way to distinguish from these two formulas, which one to use is ask yourself, are there any conservative forces? Yeah. So you've got to see if there are conservative forces or non-conservative forces in the problem. In this case, all the forces, well, there's one force which is non-conservative, the friction force. So when you see a non-conservative force, I recommend using this formula, principle of work energy. If there is a non-conservative force, conservative force like gravity, springs, and this energies, then use conservation of energy.
So I'm saying, like, this is how I understand I'm setting it up. So for some reason, like the T1, some of the works is equal to T2 is easier for me. I don't know why it is. What's like if I set it up correctly as far as like the position and direction? What's the difference in doing that? Either way, you should put the non-observed force in there. When you do the V2s and V1s, you should put the non-observed force in there.
So I probably confused it. So there are two formulas: principle of work energy and conservation of energy. Okay, how do you know which one to use in which scenario? The first thing I would look at a problem. First, I'll identify if I want to find the velocity as a function of distance. If it's a velocity as a function of distance problem, like this one is, then I will use one of these two principles. Right. Now, if draw the free body diagram, I do the free body diagram. I look at the forces on the free body diagram. The forces, there is a non-conservative force. It's the friction force. The non-conservative force is the force in which the work done depends on the path taken. Okay, while a conservative force like gravity or spring force, the energy only depends on the initial and the final position. That's a conservative force. In this case, there's a non-conservative force, Fr, friction force. That is why I use the principle of work energy. Okay. Now, what I said, and this probably confused you, is that you can also use conservation of energy on this problem in spite of the fact that there is a non-conservative force, Fr. And the reason is because the work done by Fr is zero. The reason why the work done by Fr is zero is because Fr acts at this point, which is the point of contact. But the point of contact has zero speed. So the work done by the force in moving this point, which is at zero speed, is zero. So it doesn't really matter.
Does that mean that the roll without slipping friction does no work?
Yeah, slipping. If it's slipping, friction does do work. If it's not slipping, in this case, friction doesn't do work.
But that's a simpler way to
Thank you.
Yep. So I is mr square divided by 2 pg square divided by r square. So if you simplify this, I think, oh, hold on. I think I did a mistake here. This is a sphere. This is not the inertia of a sphere. This is the inertia of a disk. So the inertia of a sphere, and this is something which will give it to you, is actually 2/5 mr square. Okay, so inertia of a sphere is this. So I need to go back and fix my I, which is here. It's 2/5 mr square. So if you simplify this, I think you get 7 divided by 10 mvg square. Okay, so I got this term, I got this term. I need to find u12. Okay, u12 is the work done by all the forces in the system. So Fr does no work because the point in contact has zero speed. This is zero speed, so F does no work. Fr does no work. The normal force also acts along this, so it does no work too because the speed is zero. The only force left then is mg. So mg does work, and the question is, what's the work done by mg? So the work done is mg times the distance moved in the vertical direction, right? Let's try to see what's the work done by the force mg. So the initial height of the center of mass from this point, you could choose any point you want to take the datum. Then it moves right here. It's the new height. So that's going to be what? R plus R cosine 45 degrees. So mg delta h is mg. This is delta h. Mg delta h is also equal to mg Okay, I also need to figure out the sign. So mgx down and delta h is down. So the sign is positive. So this is right. Okay.
I have a question.
Yeah.
Is it normal force going to work closest to 45 here?
Yeah. Okay, so putting all this together, T1 is 0. U12 is mg r plus r 1 minus cosine of 45 degrees equals 7 divided by 10 mvg square. So m's cancel off. Is r given to us? Okay, I should put this as capital R and this is small r. Yeah, this is consistent with this. Okay, so r is given is 10, small r is 0.5, so G is 32.2, 10 plus 0.5, 1 minus cosine of 45 degrees equals 7 divided by 10 Vg square. So solving for Vg gives me, I get 11.9 feet per second. Okay.
Normal force is considered conservative or non-conservative?
So what happens typically is, well, normal force is a non-conservative force, okay? Because if it was moving in the y direction, then if the normal force was some expression which was, say, nonlinear function of, it was not a constant, but some funky expression, then it will do work, which depends on the path taken. But usually what happens is a normal force, right, doesn't do work because there's no acceleration in that direction, never. So you can always treat those, you can just ignore the work done with the normal force. It's very rare to see a normal force. Well, the normal force always exists when the particle is in contact. So this work done is always zero. When it moves from the surface, there's no normal force. So there's no work done. So yeah, so ignore n when you, n should be a factor when you decide which of the two principles to apply. Okay, is that clear? Any other questions? Okay, let's do.
Problem so far, like, almost typically you could determine work done by friction.
Yes. So friction force is mu times n, and that's used to find work done. Okay, a pendulum problem. The pendulum consists of a 10 kg uniform disc and a 3 kg slender rod. If it's released from rest in the position shown, okay, clearly there is gravity, otherwise this thing is not going to move. Determine the angular velocity when it rotates clockwise by 90 degrees. So we got to find the angular velocity when the pendulum is vertical. Again, good idea to draw the free body diagram because that will help us to find if there are conservative or non-conservative forces. So I'll write this as A y because that's A, point A, AX. Let me call this M2, this one M1. So there's M1G and there's M2G. Is there anything else? Or there's a moment. So moment also. What's that?
Why are you drawing it halfway?
It's not halfway, it's just at a random angle theta. I would recommend doing that because then you can try to write the force as a function of theta and you would not do the mistake of assuming that the forces are constant. Mg changes with time. Always draw it like this. Never draw the free body diagram for the extreme position unless you have to. Especially when you're writing F equals ma. Also, another thing is sometimes you will miss some of these forces. If you had not done M1G, M2G, you would have missed that when you compute the work done. Okay, so that's the free body diagram. Now the question is, how do I go about solving this? So again, as I said, the cue is you're told to find the angular speed when the position is 90 degrees. You're given the initial position, initial velocity for the initial position, which is 0, and you're told to find the angular velocity when the position is 90 degrees. So you're trying to find angular speed as a function of theta, right? When you see that relation, I highly recommend using conservation of energy if it's conservative forces only, or work done, principle of work done, if there are non-conservative forces besides conservative forces. But if you use F equals ma, that's totally fine. You should get the right answer. So Oh yeah, absolutely. So you can see the moment there, that's constant. So because it's a constant, it turns out to be it's actually a conservative moment. It doesn't, it only depends on the initial and final position. If I change that moment to a function of theta, let me say that the m is 30 times theta, then that m becomes non-conservative because the path taken determines the work done. So in this case, actually, I would not recommend using conservation of energy just because you see that there's a force m. Now it turns out that m is nice, it's constant. But if it was not a constant, then yes, you had a non-conservative force. A good question. So as I said, method one, use F equals ma, and that should give you the answer. So you use F equals ma. In this case, you'll actually be better off if you took moments about point A, wrote the equation for the moment, which will be m equals I alpha, and then take alpha, integrate that alpha to get angular speed. So you have to do equations of motion and kinematics to solve this problem using F equals ma. So I would recommend moment about A is I about A alpha and integrate. You could try this at home. Let me do it the other way, method two. Okay, again, as I said, you have two choices, conservation of energy versus work done. Use work done, principle of work done, because that M is, it could have been a non-conservative force. So I'm going to use principle work done, which says that T1 plus U12 is T2. The initial kinetic energy is simply 0. What's the final kinetic energy? So to find the kinetic energy, I need to find which formula it belongs to. Is it linear motion only, or it's fixed axis, or it's general planar motion? It's fixed axis, right? So I'm going to use the fixed axis formula. Okay, I need to do that for two things. I need to do that for M1. So I'll write it as IO omega square, where the summation is for the two things. That's the slender rod and the mass, so M1 and M2. So for M1, okay, we'll give that to you, but it's ml squared divided by 12. That's the inertia of a slender rod, plus mass times the distance from the center of mass, which is over here. So, well, this is L. Okay, that's the L I wrote here. So mass times, so I'm using the parallel axis theorem to find the inertia about O. So it's going to be mass times the distance from the center of mass here to the pivot. So it's m L1 divided by 2 square.
The distance, isn't it even? It's 2, 1.
Oh, it's L1. Sorry, I should put L here. I just wrote it in terms of a variable L instead of, that's L, not 1. Yeah. So plus half m2, the inertia of a disk is mr squared divided by 2. To continue it on the next line, write it this way: half I omega square plus half inertia of the disk plus the inertia, well, I need to find the inertia of the disk about A. So again, I need to use the parallel axis theorem. So the inertia which I just wrote down is about this point. So to find the inertia about this is going to be L plus R. Right? That's the distance of the center of M2 from A. So M2 L plus R square is the inertia. Okay, so M1 is 3, I think. M2 is 10. L is 2. R is 0.4. So putting all that in, T2 comes out to be 31.2 omega square. And so I only need to find U12 now. U12 is the work done from going from 1 to 2. Okay. So there are 1, 2, AX, AY, there's two forces there, and then there is moment M, and then there is M1G and M2G. So there are 5 forces, and we need to find the work done into those 5 forces. Now, the work done by AX and AY is going to be 0 because the point A does not move. There is going to be work done into M because that is the work done due to rotation, and then there's going to be work done into M1 and M2. So I need to write down the work done into those 3 things. So here I go. So first is, let me do work done by M1G. Okay. The work done by M1G is simply the descent of the rod. So it's going to be L by 2, L divided by 2. And since mg is downwards and the distance moved is downwards, that's going to be a positive. So then there is work done due to m2g. So m2g moves from here to here, and this distance is L plus R. Again, that's positive because m2g is downward, L plus R is downwards. And then finally, the work done due to moment m is m times the angle, the final angle, which is pi divided by 2. The initial angle is 0. Okay, now what's the sign on this? Is it positive or negative? It's negative. Why is it negative? Uh, huh. Well, it's doing positive work though. It's going to increase the energy of the system. I think it's positive. Is there a good explanation for that? I think it's positive because it leads to so the reason why it's positive is because even if m is negative, my angle convention should be consistent with that. So 0 positive is this, and then that's going to be pi by 2 positive. So effectively it's going from 0 to minus pi by 2. So the signs actually take care of that. So if you wanted to put it with a negative sign, it's minus m minus pi by 2 minus of minus 0. That's positive. Okay. So the convention that m is positive counterclockwise is true as long as you also assume that theta is counterclockwise positive. You cannot take m to be counterclockwise positive and theta to be negative in the counterclockwise direction. So consistent way to do it is if you assume 0 to be this angle, if you like, then this angle, the angle turned in the clockwise direction, also is going to be negative. M is negative, but angle is also negative. So it's going to be minus pi by 2 and not plus pi by 2 because it's going clockwise. So negative and negative gives you positive. Okay, so I'm going to not just going to write the answer. You go and check if this is right. what I get for U12 is 312. And so if you put all this together, T1 is 0, U12 is 312 equals 31.2 omega square. Solving for omega gives me square root 10, which is 3.16 radians per second. Okay, questions? Yeah.
On the angle part, is that initial minus final or final minus?
It's always final minus initial, except that the final angle is negative because 0 is this, and I'm going clockwise, so the final angle is negative.